Hello, can you hear me okay? All right, I'm just going to get started here. So I'm using containers in a class that I teach in the USA. And I don't really use it at work, but I do use it as a teacher. So for those of you who teach, you may find this to be useful, this technique. I'm going to tell you what containers are. I'm going to tell you what exactly they were invented for, why do containers exist, and how they solved that problem that had arose. They resemble virtual machines, but they are different. So I'll try to explain how they're different. And then I'll talk about some management applications that you may have heard of that are very timely and useful. One of them is called Docker. I'll give some examples of that and I'll run it. And then I'll run another one called Kubernetes. Kubernetes is in a way like a cloud of containers. So what are containers? Why do they exist? I'll try to illustrate that with an example. We have many diverse computer targets that we might want to run applications on. We might want to run a program in the cloud. We might want to run it in a virtual machine, on a laptop, on a server, something enterprise, or something like an ordinary laptop. We might want to run an application on a different operating system, say Windows, Linux, Macintosh. These operating systems may have different versions, and they may have different libraries. If it's Linux, there may be different distributions of Linux with their own libraries. But I don't wish to worry about this mess or this plethora of different targets. I wish my application to run on all of these. And I have a lot of applications, and they're very strange, that I wish to run. Some of them are websites and databases and all sorts of things. But I want to run them on any target. So how do I do this? It's an end-to-end problem. N targets, N applications. It's a matrix. Here's an analogy to that problem. Let's say I'm transporting goods. I'm transporting stuff. Now, what I want to transport, say, from India to the USA, could be a large object or a small object. And it could be in a different quantity. Many chairs, many sofas, many televisions, they're all different sizes and they all come in a different quantity. I may want to transport for these, let's say I'm transporting this something. I may want to transport it by ship, by rail, by air, by truck, by rickshaw, I don't know. So you want to transport this stuff, and how do you do that efficiently? Given that they come in different sizes and you've got different transportation mechanisms. This problem was attacked in the last, I think, 30 or 40 years, certainly after World War II, by the invention of the shipping container, which is a standard-sized box. This standard-sized box was agreed upon by the industry as just the right size for transporting on boats, trucks, trains, etc. And once everybody agreed on the size of the shipping container, and it became much easier to transport things, because the vehicle that moves the shipping container only needs to worry about transporting shipping containers. The vehicle, the ship, or the train does not care what is inside of these shipping containers. Let's go back to software and look at the analogy. What a container is in software is like the shipping container. You can port the shipping container to your diverse operating system, and then run whatever application you would desire inside of it. The operating system only needs to know how to run the container, and then within the container you run whatever you like. This helps a lot with many things, like isolating dependencies. Well, let's say I have a library that I need to have in order to run a program. Put the library in the container. The operating system that runs the container need to know nothing about it. You can distribute applications very easily this way, and it makes testing very simple. Here's what it looks like. Well, there's the technical definition of what a container is. You can call it operating system level virtualization. And as you can see, I have two pictures here. I'm comparing containers or operating system level virtualization with traditional virtualization. On the left, we have operating system level virtualization, where 3 containers are running on top of the kernel. Notice that there's just one kernel here, but 3 containers. On the right, we have the old-fashioned mechanisms. 3 virtual machines, each with their own kernel. So they seem to be very similar, these containers and virtual machines. How are they different? First, the container takes up a lot less memory. For one thing, you don't have to have the kernel in the container. You do not have the kernel in the container. It's, by definition, operating system level virtualization means you don't carry that. So it's a much smaller footprint. It starts immediately because there's less software to load. It's somewhat easier to maintain because you're not maintaining a whole virtual machine with the kernel and all the associated trappings. You're basically just taking the container and the application inside it. And because it's so much smaller, you can run many more of them on the server. Let's say you have a virtual machine. The virtual machine may require 10 to 20 gig of storage and other resources off your server. You may only be able to fit in the tens of number of virtual machines on your server, whereas containers you can have many, many more, hundreds or even thousands. It's more scaling processes rather than physical resources. But you do need virtual machines for some things. Virtual machines are good because they are general infrastructure. You can do anything with a virtual machine that you can do with a computer for the most part. Not so with containers. In fact, containers generally are good for single-purpose items. And I'll talk more about that in a moment. So, digging a little deeper into what a container is. Container is an isolated work environment. It has its own file namespace, which means that a file accessed within a container would not be visible outside the container. And you cannot see files necessarily outside the container from within the container. It's isolated. It has its own network address. So you can run hundreds of containers on your server, and each would get its own IP address. Maybe it's a private IP address that's not visible on the network, so it's a private network, but still it has its own IP address. And you can give it its own physical resources, that is, its own CPU and memory allotment. And how is this accomplished? Well, those of you who are familiar with Unix know that there's a concept called a process group. So when you tie some commands together, maybe one command piped into another, you've created a process group. Let's say I do ls pipe word count minus L. The two processes are created but they are in a single process group. What is a single process group? That means that if you send a signal to it, every process within the group will receive it. What does that mean? That means I can all stop them all together, I can put them to sleep all together, or I could kill them all together. So that's the first building block of containers. You collect processes together into a group. But it's not enough. You need a little more. In the aughts, in the 2005 timeframe, a new feature was introduced, I believe by Google, into the kernel, the Linux kernel, which took the concept of process groups and beefed it up a little bit more to give resource allocation so that you could give a certain slice of CPU time and memory and other important resources to the process group. This is not the same thing as a process group, but the concept's very similar. You can also do some other nifty stuff, like freezing a group of processes and then waking it up later. The third building block that is useful for containers is something called Chroot. This is namespace isolation. This means, all right, so you have in a hierarchical file system a notion of the uppermost or root level, or slash. That's the root. In the triangles below, I've run the chroot command to make it so my root is var lib docker container 1. Once that's done, I can't go above that level in the hierarchy. I can't see any files above there. I've effectively isolated the namespace, the files, that is to say, the files that are visible to me. So those three building blocks together give you an idea of the capabilities. So next, once we have the technical stuff out of the way, we need a way to use this easily, and that's where Docker comes in. Docker is a famous company at this point because what they've done is they've made containers easy to use. What Docker does is it makes it simple to build containers and run them. And also it has a repository in the cloud where there are tens of thousands, or not millions, of containers pre-built by other people. So you can download a container to do pretty much anything. And I'll demonstrate that in a moment. Even though we don't have internet, I have some on my machine already. Docker also sets up the network and makes it easy for Docker containers to talk to each other. Some of the software-defined networking concepts which were introduced in the previous talk come up in containers. Containers also have solved the problem of speaking to each other, and there is a software bridge and a gateway to go out to the external internet. So, Docker concepts. First, I'll explain two Docker concepts. I'm not going to tell you how to run Docker. I'll just give some examples so you'll get the flavor of it. An image in Docker speak is basically a pre-built container which you can use to instantiate real containers. So you might have a Linux image, and you can create containers from that template. You can say, search for a particular application which you wish to run. Let's say an Apache web server. You can go to Docker's cloud repository and search for that, and you'll find an image which you could download. And then once you have that image, you can create as many containers as you wish. Here's an example where I've searched for Debian images. I did Docker search Debian, and it gave me a list of all these different containers that people have built. So there's some interesting things here, like who made these containers? Which are official? Maybe do they have some hacker who's put a bad container up there? I think that's what the column official means. And also there's a rating system. Once you have downloaded an image, you can create a container. And then you can list the images. I've downloaded a few right there. I think I'll jump right into our demo now. So this is our first demo of the day. Let's see how this goes. Okay. All right. Okay, so I've listed, thanks you, Joseph, for your support. So we have two images which I've downloaded. So I'm going to now create a container out of these images. These are CentOS 7 images. I'm going to create a container, and it's going to run the bash shell. The IT stands for interactive. I'm giving it a name. Now I'm inside the container. Oh, darn it. It has an IP address, but I haven't downloaded the NetTools package, so I can't see it, but it does have an IP address. Notice I'm running on Macintosh, so here we are in Linux all of a sudden. Notice how quick it took to start. There's /proc with all the bells and whistles there. Okay, let's get out of this and try something else. Next, what I'm going to do is I'm going to send some information into the container. Sometimes when you start up a container, you want to give it some additional information. And the nice way to do that is with environment variables. Environment variables come in the form key equals value. You'll see the -e option there. And I've created an environment variable called parm1, and I've given it the value, my parm. Let's see how that goes. Okay, I've entered the container. And there we have an environment variable. Now, a clever software engineer could use that information to customize however he or she wished. Docker ps -a shows you what containers exist. You'll notice I removed one a moment ago. One more thing I'll show you, then we'll get back. So I restarted that container. I'm in it now. Proc VM sys. then drop. That's it. Okay, good. Okay, what went wrong here? So I have tried to do something that would affect something outside of the container. I have tried to exit the container and touch something on the operating system. This often happens when you're doing things with containers. You are stuck inside the container. Some people call it a jail. But every now and then, you have to do something external to the container, and like in this case, you find your container to be weakened as a result. So how can I give this container the privileges it needs to do a particular operation? One way to do it, and this is a heavy-handed way that's really not that great, is to give the container privilege mode. What privilege mode does, essentially, is give it a super user type ability. Oh. That time, no error. The privilege mode worked, but there's a lot of things that I can do now. It's super user mode, so I can actually cause a lot of damage. And this leads to a criticism of containers. There isn't really a good security architecture for them at the moment. Right, so that's a little bit of a flavor of how containers work. Now, what I did was I started bash shell interactively inside of it. In fact, containers do not normally work that way. What you normally want to do with a container is run a single thing. In fact, containers work best when they're what's called stateless. That means they're ephemeral. They don't store anything. They run and then they can go away without a trace. This is how they're used, for example, typically, as far as I know, inside of Google's cloud. Google is one of the main proponents of containers, and that's what they use in their data centers. They don't spin up virtual machines, they spin up containers. Containers can disappear, they can come and they go. So the way I used it was different than that. I tried to use it as a bash shell. And going back to where I got into this for my classes that I teach, why do I start using containers? Why don't I use virtual machines? I wish to give students computers, infrastructure. I don't want to give them a single service. The answer is, when I was told to teach a course, I said I needed a machine. Well, they gave me one with only 4 gig of memory. It wasn't enough for 30 students. So I couldn't divide that 4 gig of memory into virtual machines. There just wasn't big enough. I ended up using Docker, and actually that worked just fine for that particular class and for those particular situation I was in. So I was using Docker not as it's typically used. I was using it as infrastructure. But normally it's used for applications. And this leads to the critical difference between virtual machines and containers. So as a service is a term you may have heard of. What it means is self-service. Somebody can come along externally and go to, say, a cloud service and take that service themselves. they don't have to go to an administrator as a go-between. They can go directly to the service and they can start using it. So you could go fire up your own virtual machine or fire up your own cloud. Another aspect of such services is that they can scale really well and they're remotely accessible. So that's sort of like what a cloud service is. Infrastructure as a service means virtual machines as a service. They're remotely accessible. You can spin up as many as you want, so they're scalable, and you don't need an administrator as a go-between. You can service them yourself. That's infrastructure as a service, and that's what we normally think of as the cloud and virtual machines. Platform as a service is what containers are good at, because platform as a service basically means applications. You spin up not a virtual machine, not raw infrastructure, but a program, an application which does something, like an Apache server. So when you think of containers, typically you should think about applications. When you think about virtual machines, you probably are more thinking along the lines of infrastructure in the cloud. Lastly, one more term. In addition to Docker, an essential management item useful for containers is something called Kubernetes. It is somewhat analogous to OpenStack, which is a cloud. Think of it in a way, as a cloud management system for containers. But remember, you're not spawning up infrastructure here. You're spawning up little programs, little applications. So imagine those little green dots, those little green squares. Those little green squares could be Apache web servers, and what you're doing is spawning up more green squares in order to handle an increased load to your website. What Kubernetes does is manage this all for you. It'll select what virtual machine or real physical machine to run these containers on, etc. And it will also coordinate communication between groups of containers, say one group in charge with handling web accesses and another group charged with, say, managing a database, etc. All those plumbing can be helped with Kubernetes. That's a little introduction to containers. Thank you very much.
So with any kind of virtualization, the first thing that comes to mind is the quality of service, so that no bursty client, virtual client, can really starve the whole infra. So do we have something like that in containers or for containers? Might be on the disk side, network side, compute side. So do we have a control on these containers?
I think that would go under the C groups component of the infrastructure. The C groups do allow you, I believe, a ceiling of how much of a resource you can take. So no more than a certain amount of CPU or disk, etc. I don't believe they give you a floor, which means a minimum CPU, which is kind of interesting. As far as quality of service, I don't know the exact answer, but I think, as far as like say CPU scheduling or whatever, Linux components could be leveraged for that.
Yeah, right. But they are very generic to all applications that is running on Linux.
Yeah.
Right. So nothing particular to containers, where you're controlling containers which are contesting for all these resources.
Beyond the C group's floor and ceiling, which is sort of a heavy-handed thing.
Right.
It's not as fine-grained as quality of service. I haven't heard anything, but I wouldn't be surprised if people are thinking about that and increasing the capabilities of C groups.
Okay.
So, Dan, is it worth to talk about the shared volume concept in Docker? Especially like what I do is normally in my development environment, I expose the uh, code base as a shared volume to my Docker containers, which help me to build the code in different Docker containers at a given point of time, even though I have to change the code only once.
Sorry, I didn't
So-
get the question, Nathan.
Yeah, so basically in Docker container, right, there is a concept called shared volume, which you can expose to the container. So it's basically a shared path which you are exposing to different containers. So what I do for my normal development activities is I launch a container exposing the code path which I normally use in my host machine. So the way it helps me, like I don't have to do the changes in different nodes, different containers. I can do it only in one place, but that same thing gets reflected to whatever or how many number of containers I have launched, and I can build that up. So I find that very a kind of very cool feature in containers, especially when you are running your code base in containers. Yeah, it is there. Yeah.
So that how they do it is, I mean, it might be different for VirtualBox or KVM or containers, because the level of virtualization is completely different. It would be pretty easier for the containers to do because they have the same operating systems.
Yeah, I didn't demo sharing between the host and the container. I didn't demo that. However, it's remarkable how easy it is. I agree. It's very convenient. And I think the container philosophy is not to store anything in the container. You should be able to kill the container and not lose any data. So you want to link your storage to the container through like the mechanism you just mentioned.
About containers and Dockers, right? In the concept of OpenStack, what we have is basically block storage and object storage. So whenever we are initializing in VM or something, the disk volume, the database is all contained in the object storage. So how do you differentiate between those containers and block storage?
If you're asking how can I expose to a container, say, a block storage device, or expose to the container an object storage device? So one mechanism is the one that Atten just mentioned, which would be a file system access point. A block storage device. I believe the /dev directory is not by default available to the container without privilege mode, but I'd have to check on that. As far as object storage, I think you'd be talking about a REST interface, just internet network packets. And those would be simply through the network. And what you can do is you can map a particular port. So if the REST, if your object storage always listens on port X, but that you can map that port to your container. So that's just over simple network traffic, which is easiest of all.
So the block storage part, if you're thinking of block storage device like iSCSI, that would be pretty easy for the Docker because you just have to do that. Right? Anything that comes to the IP will be passed through. But SCSI is something which I'm not aware of, which you need to look deeper into it. But once you get the IP, I think you're.
In that, I saw that the containers are being aggregated using VMs. Is there a particular reason why you're doing that? Do you need like a separate kernel for that? Is that the reason why you're doing that? Or if not, then why can't we just use containers, which are obviously live?
I think that's a fair statement. It probably would have been a clearer slide if I used physical servers there, rather than having multiple levels of virtualization. But if, now remember, they solve different problems. containers are good for scaling applications. They're platform as a service, whereas infrastructure as a service is raw machines. You may have a situation where you need both. And you may be going to, say, Amazon. And as you scale up your infrastructure, that means you add virtual machines, you are all at the same time scaling up your applications using containers. So you may be doing both. But I think a more natural way to look at it is with physical machines. That's clearer in the slide, probably. All right, I think we're done. So, goodbye, everyone.